So hold on, what is this Gauss term? Well, it was created by this guy. He's a German mathematician, astronomer, geodesist, and physicist. Look at his fancy signature. Imagine you want to estimate the number of people in a stadium. Smart way to do it would be to count the number of tickets sold, but for some reason someone forgot to do the important bookkeeping. Remember kids, always be good with bookkeeping. So how do we estimate the number of people in this stadium? You could divide the stadium into sections like cells in a mesh, estimate the average number of people per section, multiply the average by the number of sections. This is basically what Gauss does in the finite volume method. In the context of fvSchemes, Gauss essentially refers to Gauss divergence theorem, which is used to relate the volume integrals to surface integrals. In the finite volume method, variables like velocity, pressure, temperature are typically stored at the center of each cell. To calculate things like flow through boundaries of a cell, things like how much fluid is flowing from one cell to another, you need to know values on the faces of these cells. The Gauss keyword tells OpenFOAM to use a particular approach based on the Gauss theorem to approximate the value of a quantity, like a gradient or a divergence, at the center of a cell, using the values at the faces of the cell. Gauss theorem effectively allows us to integrate the quantity over the surface of the cell instead of calculating something directly inside the cell. So in essence, you take the values at faces, perform surface integration, and get the values at the cell centers. Let us take an example of pressure gradient in the fvSchemes. This term is a gradient term and hence must be specified in the grad schemes subdictionary in the file. The Gauss term that we see right here, this is the Gauss theorem used to approximate the pressure gradient delta P at the center of each cell. The next term that we have, this is linear, uses the linear interpolation to estimate the pressure at the faces of the cell from pressure values at the centers of neighboring cells. Linear interpolation assumes pressure changes linearly between cell centers. Ultimately, we have the corrected term. This applies a non-orthogonal correction to account for the fact that the cell faces may not be perfectly perpendicular to the line connecting the cell centers. This helps improve accuracy on skewed meshes. So, why Gauss? Well, it is physically and fundamentally a well-established way to apply the finite volume method. It helps ensure the simulation conserves the physical quantities because we are integrating the fluxes across cell boundaries, essentially keeping track of the ins and outs. It is also quite versatile in that it can be combined with different interpolation schemes and correction methods to achieve different levels of accuracy and stability.